Alright, so the goal here is to find an expression for the area under the curve using limits. So that means we need to have this general formula with sigma notation. It looks like this. Sigma I equals 1 of f of xi delta x, and we're doing this for, let me see, n subintervals, and we're taking the limit as n goes to infinity. Okay, so let's talk about what all this stuff means. Okay, so delta, so let's say you have a curve. So you have a curve looks like this. Alright, so our curve looks like, let's say it looks like that. Alright, so we're trying to get the area under the curve. So we're trying to get this area that's right here. And the way we're going to do that is by adding up a bunch of little tiny rectangles. Okay, so like, let's say rectangles like this. Oops. Like that. And let's say we're going to do that from some interval. So let's say from 1 to 3. Alright, well, then we'll be starting from here, 1, and be going to 3. Well, let's just say that 3 is here. And in this case, we have 1, 2, 3, 4 intervals. So in this case, n is 4. But in this problem here, we're saying n is infinity, which means that we have infinitely many little rectangles. And when we have infinitely many rectangles, then when they're cut up into infinitely many pieces, you're not going to have this overage right here, or depending on how you do it, like shortage. So since those rectangles will be really small, it'll most likely it'll be like this. That'll be one rectangle, and that'll be the other, and that'll be the other, and that'll be the other, and they'd be really, 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 really tiny. So you don't have to worry about it being inaccurate. It'll be right on that line right there. Okay, so that's what this means, right? Infinitely many subintervals. All right, and then that ends right there. So that means that if you're running into infinity, if you're taking the limit as n goes to infinity, that means you're doing this infinitely many times. Also, that means you're gonna add up. You're gonna do your summation infinitely many times. Okay. Now, what this means right here is the width of your subinterval, delta x. So that means how far apart these guys are right here. Okay, and the way you determine that is through this formula. Delta x equals, oops, I forgot my x. Delta x equals b minus a over n. Okay, so you can determine the width of your intervals depending on your, I guess your domain, like where are you doing this from. So we're doing it from there to there. So let's forget about n going to infinity for right now. Let's just say we're going from 1 to 3. All right, so let's say we're going from 1 to 3, and we want to cut this thing up into 1, 2, 3, 4 subintervals. All right, so we would go delta x equals 3. Well, this is A is our beginning part of our domain, right? And B is the end part of our domain. So we're going from A to B. I guess another way to say it is you could say that x goes from 1 to 3, which is meaning that x goes from A to B. All right? So we're going from there to there. So then you go B minus A. So B minus A basically tells you what that distance is, what that positive distance is. So B is 3. So 3 minus 1, that's A is 1, over N. Well, we want to have 1, 2, 3, 4 subintervals, so 4. So you get 3 minus 1, which is 2, over 4, which reduces down to 1/2. All right, that means that each one of these widths is 1/2. So that's 1/2, that's 1/2, that's 1/2, and that's 1/2, right? And so 1 plus 1/2 is 1.5, plus 1/2 is 2, plus 1/2 is 2.5, plus 1/2 is 3. Okay, so if you're taking this to infinity, that just means you're going to have a smaller delta x, right? If you're going to have infinitely many subintervals, then your delta x is going to be smaller. That also means that your delta x is going to have an n in it, right? So if we're taking this to infinitely many subintervals, our delta x can't be like a constant. It has to have an n in it to reflect the fact that we're going to that many subintervals. Which means also that if you were actually doing a fixed number of subintervals, right, you would have this n right here. So there's n, there's your n. It was a numerical n because in this original problem I said, well, in this example of my example, I said that we were going to do 4 subintervals. But now we're going to do n subintervals, but we're going to say that we're going to take n to infinity. Okay, so with that in mind, let's thought bubble kind of like this whole thing right here. Okay, back to our problem. Well, we know here that we're going to go from 1 to 3. Well, that means that that's our A and that's our B. Great. So that means that we have delta x equals our B minus A, so it'll be our 3 from right here, right? Our 3 minus 1 over n. All right, so delta x equals 3 minus 1, which is 2, 2 over n. Great, so now we have our delta x. So let's go ahead and kind of rewrite this right here. So we have the limit as n goes to infinity. The sum, or sigma, I equals 1, n, and I know we have f of xi times delta x, but I know delta x. Delta x is a little bit times there, times 2 over n. Delta x is 2 over n. So that is that. Before I continue, this xi bit right here, that xi, in case I didn't mention it, I don't remember if I mentioned it, that represents your height. Your height, not your height, the input that corresponds to your height. Right? So that's going to represent what you would be putting in to the function, that would yield the height of your rectangle. And that would be, I'm going to put right here, it's not any value, by the way. It's a specific value. It's a smart value. Right? You wouldn't be putting in every possible little tiny value here. You'd be putting in specific values that correspond to the next subinterval. So, for example, let me draw the graph again. And let's say, I'll just kind of draw the rectangles like this, even though if you're doing infinitely many times, it's not going to like have that overhang part. So x, like x1, if it's x, so you see here there's xi, right? All right, so let's say I is 1. So x, oops, x1, that's a 1, would be this location that corresponds to that height. And x2 would be this location that corresponds to that height. See? So you're not going to say like x2 is right here. That's within the same rectangle. That's what I meant, a smart value. It's a smart value, which is basically an x location in an adjacent rectangle. See, so x sub 3 would be right there. Of course, since we're doing infinitely many rectangles, those guys would actually be really close to each other. Also, I just want to mention that this right here represents the height of the rectangle, and this represents the width of the rectangle. Right? So the height of the rectangle would be this right here, and the width of the rectangle would be this right here. So basically, together, these two guys right here represent the area of the rectangle. I mean, just this area, this right here is the area of one rectangle. But this means here that we're going to add up all our rectangles, and this means here how many rectangles we're doing, but we're going to do infinitely many rectangles. All right, so this means we're going to be adding up infinitely many rectangles within a certain domain, and in this case it's going to be between 1 and 3. Okay. All right, so remember we said that right here in blue, x sub I is a smart value. We're going to say that x sub I is equal to a plus delta x. Okay, I'm going to highlight that. Okay, so we're going to actually pick where we're going to mark the, how should I put this? How we're going to pick the x value that corresponds to the height of a rectangle. So even though it needs to be within the interval, so we're actually going to make it the right spot. We're going to make it the right most part of that rectangle. You could make it the left part, but we're going to make it the right part, right here. Okay, and all that means is that this right here is A. And then this gap right here, so right here, that little gap right there, that little move, is delta x. You see? So A plus delta x. Okay, so A plus your width will get you to this location right here. So f of A plus delta x is this height right here, right? And likewise, f of A plus 2 delta x would be this height right here, would be this location here, which would correspond to over here. And this would be your x2. So your x2 would be f of A plus 2 delta x. All right, so let's go back over here. So we're going to say that this location, that xi right here, we're going to say is A plus delta x. All right, great. Well, we know our function. Our function is right here. And we also know our delta x. Our delta x is right here. And we also know our a. Our a is right here. All right, so I'm going to rewrite that function. So f of x equals 2x over x squared plus 1. Okay. Now, wait 1 second. Put this back where it was right there. So everywhere you see an x, I'm going to write parentheses there instead. So I'm going to erase this x, put parentheses. I'm going to erase this x, put parentheses, put bigger parentheses. Okay. Since what's supposed to go in here is xi, right there. So basically we're transforming this to, instead of f of x, f of xi. So we're making it f of smart value, not of any x, but f of smart value, which corresponds to these smart values right here. Okay, so that means that I get to change this to f of x sub I. F of x sub I. All right. And I know that right here, the x sub I is a plus delta x. So in here, I'm going to write a plus delta x. And here, I'm going to write a plus delta x. Okay, well, I'm going to go over here. And I'm going to say, well, all right, so f of x sub I is equal to 2 times, well, I know what my a is. A is that guy right there, which is that guy right there. All right, so 2 times 1 plus, I also know delta x right here, 2 over n. 2 over n, all right, over, and then right here, a plus delta x, which is it's the same exact thing, right? So it's 1 plus 2 over n squared. So same thing as that, because they're both a plus delta x, right? Plus 1. Cool. So then I'm going to go ahead and just highlight this, because that is the same as that, which is the same as that, which is the same as that. All right. Now I don't just have f of x, I have fancy f of x sub I. Okay, so then I can put the whole thing together. Time to rewrite this guy, this thing right here. This limit, but now it's specific to our function and uses fancy f of x I. So we're plugging in smart values, not just any value. Okay. And also, built into this equation will actually be our what's it called? Our like domain, from our A to B. So it'll give us, it won't just give us like infinite area under the curve. It's going to give us the area under the curve from 1 to 3, because in this formula we have we basically coded the domain. All right, so here goes. So you have limit, or in the formula, I guess, like that restriction is in there. As n approaches infinity, I'm just basically copying this down, of the sum is I, starting from I equals 1 to n, to this stuff that I just got right here, which is my f of xi. So 2 times 1 plus 2 over n over 1 plus 2 over n squared plus 1. Okay, I have that. Then I'm going to do my delta x, which is times 2 over n. Okay, and it's almost done. There's something I forgot. I have to include an I. Okay, so that implies like if I is 1, we're talking about this location. If I is 2, we're talking about this location. If I is 3, we're talking about this location. All right, so you have to have an I right here, and basically with your delta x value. So there's my delta x, there's my other delta x, so that means there's an I that goes right here, and an I that goes right there. And that's because this is f of x of I. So you can do, so f of x of sub 1 would just be literally, this i's would be 1, right? And then it would just be on the top 2 times the quantity of 1 plus 2 times 1, which is 2 over n closed, times 1 over 2 times 1 over n, when that quantity squared plus 1 times 2 over n. If you wanted, and that would give you just that part would give you the area, this part here, of the first rectangle. If you want the area of the second rectangle, you would just put a 2 for I. And this notation right here means you're going to add up all those areas. And you're going to do that for infinitely many subintervals. And the domain of from 1 to 3 is hidden inside this formula. And this is the answer. And I'm going to highlight those I's that are right there. There and there.